Hello and welcome back to the session. Okay, let's dive right into this because we have a lot of highly valuable ground to cover today. If you are currently studying Cambridge AS and A-level computer science, specifically syllabus 9618, though these strategies absolutely scale across syllabuses 0417, 0478, 0983, 0984, and 2210, you already know that the exams can be brutal. Specifically, writing code to satisfy goals using facts and rules, it can feel incredibly daunting. You might be staring at these massive, complex problem statements on the exam paper. The clock is ticking down and you're just wondering where to even begin. I want you to picture two specific types of students. Let's call the first one Alex. Alex is brilliant at memorizing. Alex overloads every single answer with raw computer science facts, dumping everything they know onto the page but includes absolutely zero analysis. Then you have Sam. Sam knows the material, but Sam rushes. The adrenaline hits, Sam completely misses the specific command word requirements and starts answering a question the examiner didn't even ask. Both of these students lose massive, easy marks, and their papers come back covered in red ink. Well, today we are acting as your master architects. We are going to decode the senior examiner's rubric to stop you from making Alex and Sam's mistakes. We are going to design your approach so that every single paragraph and every single line of pseudocode you write becomes an absolute structural masterpiece.
To get us to that master architect level, we have a very clear, structured roadmap for today's explainer. In Section 1, we'll cover the core exam principles, the underlying psychology of what the examiner actually wants from you. In Section 2, we're going to break down the procedural framework, giving you a repeatable system. Section 3 is all about evaluating algorithm quality, which is where the top-tier marks hide. And finally, Section 4 will cover critical examiner warnings pulled directly from Cambridge's own post-exam reports.
Let's move right into Section 1. Core exam principles. We need to lay the theoretical foundations before we start pouring the concrete of our code.
When the senior examiners are grading your paper, they are explicitly looking for something called conceptual understanding. Now, notice that they do not say memorizing code snippets. They specifically define this concept as connected knowledge that is entirely transferable to unfamiliar contexts. This is exactly where our student Alex goes wrong. Rote memorization absolutely fails here. You might know the theory of a sorting algorithm perfectly, or you might have memorized every single logic rule from your textbook, but if you cannot adapt that textbook knowledge to a completely brand new, totally weird scenario or a unique set of facts and rules presented in that specific exam paper, you simply won't get the marks. Top-performing candidates don't treat their brain like a filing cabinet. They treat their knowledge like a flexible toolkit. They are ready to adapt and apply their tools to absolutely any architectural challenge the exam throws at them, no matter how unfamiliar the context might initially seem.
And this connected knowledge idea ties perfectly to a vital insight we pulled directly from the principal examiner reports. They state, quote, "Candidates referencing cross-topic connections achieve significantly higher marks." Listen, the Cambridge Computer Science syllabus is not a collection of isolated islands. Your ability to write code using facts and rules is deeply inherently connected to other modules like data representation, hardware architecture, and logic gates. The theoretical architecture of your answer rests heavily on integration. For example, if you are writing a rule-based algorithm for a temperature control system, acknowledging how the analog sensor data is represented digitally before your code even processes it is a massive flex. When you show the examiner that you genuinely understand the causal relationships between these entirely different topics, you elevate your answer from average to absolutely exceptional.
So the crucial point we really need to drive home here is understanding the difference between superficial breadth and analytical depth. Academic benchmarks for this specific exam require highly logical, structured reasoning. An average candidate, like Alex, will see a question and try to shotgun every single computer science fact they know onto the page, hoping something sticks. That is superficial breadth. The top score, however, provides analytical depth. They don't just dump facts, they logically and rigorously apply a structured analysis to the specific facts and rules provided in the prompt. How do they do this? They use frameworks, like the PEL framework: point, evidence, explanation, and link. They make a solid point, they back it up with evidence from the given code or scenario, they explain the computer science theory behind it, and they link it directly back to the question asked. They build an argument, step by specific step. Now, before we continue and dive into the exact procedural steps to achieve this, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's keep this momentum going and move into Section 2, the procedural framework. This is your technical methodology. This is exactly what you do the second you are allowed to open that exam paper. We are going to give you the exact 5-step procedural framework you must use when tackling these highly complex coding examination questions. Step 1. Deconstruct the question. This is where Sam messed up. You have to deconstruct the exact command words. Describe requires a completely different answer than evaluate or compare. Step 2. Extract relevant data. You need to isolate the very specific facts, rules, and variables the examiner has provided in the preamble. Step 3. Select the analytical framework or the algorithm that fits best. Step 4. Execute with clear, precise notation. Don't get sloppy with your syntax just because you're in a rush. And finally, Step 5. Present your final answer using the correct formal computer science terminology. No slang, no vague descriptions. If you follow these 5 steps sequentially every single time, you construct an unshakable, bulletproof answer.
To help you lock this in permanently, we have a memory hack for you. It's DESEP. Just remember the acronym DESEP. Deconstruct, extract, select, execute, present. Listen, when you are sitting in that exam hall, the clock is ticking, the invigilator is walking up and down the aisles, the pressure is immense, and your brain might just freeze. It happens to the best of us. When that panic sets in, you have to rely on the blueprint. Literally, write DESEP at the very top of your scratch paper. Let it visually guide you through the noise of complex binary representations or incredibly convoluted goal satisfaction problems. It forces you to slow down, stop acting like Sam, and build your answers systematically.
So what does the execute step of DESEP actually look like to the examiner? It requires incredibly clear algorithmic thinking. First, this means step-by-step decomposition of the problem, breaking a massive, terrifying problem down into tiny manageable subroutines. Second, it requires appropriate data structure selection. Please don't just default to an array because it's easy, especially if a linked list, a dictionary, or a binary tree actually makes significantly more sense for the facts given in the scenario. Third, it demands efficient code implementation. And crucially, fourth, an understanding of rigorous testing strategies, like dry running with a trace cable, to mathematically ensure your written rules actually satisfy the stated goals of the question.
Which brings us seamlessly into Section 3, Evaluating Algorithm Quality. Let's look at the evaluation insights, because this is where the A stars are truly separated from the B's and C's.
There is a stark, undeniable difference between average and top-tier evaluation. When asked to evaluate or compare algorithms, say comparing a linear search with a binary search, an average answer just identifies basic similarities. But a top-scoring analysis, a real structural masterpiece, identifies similarities and differences. Furthermore, they use highly specific comparative connectives. We are talking about words like whereas, conversely, on the other hand, or in contrast. They don't just say one is faster, they back up every single comparison with solid mathematical evidence from the scenario, drawing clear, definitive conclusions about the relative importance of their findings. They are essentially applying that Peel framework, point, evidence, explanation, link, to their code evaluation, transforming red pen marks into green check marks.
When you are evaluating the quality of an algorithm based on facts and rules, you need a strict technical checklist in your head. The syllabus explicitly requires you to identify and evaluate time complexity, which is big O notation, right? It's how long your solution takes to run as the volume of data grows exponentially. You must also consider space complexity, exactly how much system memory your code is going to consume. You need to identify edge cases, and finally, evaluate the overall effect on systemic performance. If you rigorously discuss these 4 specific elements in your evaluation paragraphs, you're speaking the examiner's exact language. Now, stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's get back into it. This brings us to a massive psychological relief for many students, something we call the method mark strategy. Please, I want you to burn this into your memory. Marks are heavily awarded for demonstrating the correct process. Imagine a complex data source on the exam and a timer is ticking down. You're trying to extract a core trend. Even if your final code doesn't compile perfectly in your head, or your final variable output is slightly off due to a minor arithmetic error, showing the step-by-step decomposition and the correct logical process secures you crucial life-saving method marks. Never ever leave a coding question blank. Build the architecture of your answer. Show you're working clearly. Write out your logic and claim every single one of those process marks.
And to ensure those process marks translate into top grades, you need to lean on these 4 pillars of evaluative thinking.
Top-scoring candidates don't just arrogantly present one single solution as absolute perfection. No, they actively consider multiple solutions. They deeply analyze the trade-offs between them. For instance, acknowledging that they are explicitly trading space efficiency for time efficiency by using a specific caching variable. They explicitly acknowledge the limitations of their own code, maybe pointing out how it would fail if the dataset tripled in size. And most importantly, they justify every single decision with hard evidence derived directly from the prompt. This is how you demonstrate an incredibly mature, conceptual computer science understanding to the person marking your paper.
We are on the home stretch now. Let's transition into Section 4, Critical Examiner Warnings. We are going to look at the absolute most common, fatal mistakes students make year after year. So, here is the million-dollar question for you. Where do most students lose easy marks? You've spent months studying the theory. You've memorized all the standard sorting and searching algorithms. You've done homework. Yet the final grade just isn't reflecting your monumental effort. Why? The senior examiners and Cambridge subject specialists have actually highlighted 3 glaring, repetitive issues that ruin otherwise brilliant computer science papers year after year.
Here are the top 3 mistakes pulled directly from the examiner reports. Pay close attention so you don't repeat them. Number 1, using the wrong formula or algorithm for the wrong context. Just because you know an algorithm doesn't mean it's the right tool for the job. You can't use a hammer to turn a screw. Number 2, students consistently forget to check boundary conditions and edge cases. If you don't test what happens when your variable is 0, or a negative number, or hits the absolute maximum array size, your code is fragile and it immediately breaks the rules of the system you were trying to model. And number 3, the absolute biggest offender of them all, giving generic answers that are not specific to the unique context given in the question.
We need to put a giant flashing red flag on that last point. Examiner alert. The absolute classic mistake in this syllabus is providing generic, textbook answers. If the exam paper asks you to write code to satisfy goals for a library management system, your variables, your if statements, your rules, and your evaluation must explicitly reference books, borrowers, late fees, and due dates. Do not just use X and Y as variables if the prompt gives you real-world data. Always, always link every single point and piece of logic back to the specific scenario provided in the prompt. This requires a time management matrix. You must dedicate the first few minutes simply to reading and absorbing the scenario before you ever pick up your pen to write. Context is the definitive key that unlocks full marks.
So, as we wrap up this session, I want to leave you with this final, provocative question to reflect on. Go look at your past paper practice tonight. Are your answers generic fact dumps like Alex? Are they rushed, panicked messes like Sam? Or are they structural masterpieces, utilizing command word decoding and the Peel framework, built specifically for the unique scenario you've been given? Next time you sit down to practice, use that DESIX framework, deconstruct the context, extract the rules, and design an answer that a Cambridge examiner literally cannot help but reward. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep building those perfect answers, and I'll see you in the next one.